All right, now we want to talk a little bit about definite integrals. To define the definite integral, consider the following limit. The limit of the norm approaches 0 of the Riemann sum equals L. Now, L implies that the limit is a finite number. It doesn't go off to infinity or negative infinity. So if f is defined on the closed interval a to b, and the limit of the Riemann sums over the partition exists, as described above, so it equals L, in f, then f is said to be integrable on a to b, and the limit is denoted by, this is the integral symbol from a to b of f of x dx. This limit is called the definite integral of f from a to b. The number a is the lower limit of integration, and the number b is the upper limit of integration. So a and b are the same a and b that you have from your interval. All right? It is not a coincidence that the notation used for definite integrals is similar. In other words, it uses an elongated s instead of a Greek letter s, and it has a dx here instead of a delta x. Okay, it's important to see that the definite integrals and indefinite integrals are different concepts, however. A definite integral is a number which informally kind of defines the area under a curve, whereas an indefinite integral is a family of functions. It gives you a function. Okay, though Riemann sums were defined for functions with very few restrictions, a sufficient condition for a function f to be integrable on a to b is that it's continuous. So if a function is continuous on a closed interval, then it is integrable on the closed interval. That is, the definite integral from a to b of f of x dx exists. Okay? Now, if an integral exists, it does not necessarily imply that the function that you're integrating is continuous. But if the function that you're trying to integrate is continuous, then you can integrate it. That's what that's saying. So evaluate the definite integral from -2 to 1 of 2x dx. So the function is 2x. It's integrable on the interval -2 to 1 because it's continuous. Moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit. So for convenience sake, we're going to subdivide it into intervals of equal width. It's usually easier to do equal width. Way back at the beginning of the section when we showed an example with unequal widths, that was just to prove the fact that you could still do it if the subintervals didn't have the same width. But for computational purposes, it's easier if you have subintervals of equal width. So it's b minus a over n, which would be 3 over n. So 1 minus -2 is 3 over n, where n represents the number of rectangles. Choosing ci as the right endpoint of each interval produces, remember, to get ci, if you want right endpoints, you start at the beginning of your interval and add I times your delta x. And as you go up each I, that's going to be the right endpoint of whatever rectangle. So like if I was 1, that'd be the right endpoint of your first rectangle. If I is 2, that'd be the right endpoint of your second rectangle, and so forth and so on. Okay, so if I plug in what these values are, a is -2, so it's -2 plus I times delta x. Delta x was 3 over n, so it's going to be I times 3 over n, or 3i over n. So it's -2 plus 3i over n. That's my ci. So the definite integral is the limit of the Riemann sum. So just plug in what you have. So it's, remember, the function was 2x. So if I do f of ci, that's going to be 2 times ci. And we found ci to be -2 plus 3i over n times delta x, which is 3 over n. Okay, if I distribute and factor out the 6 over n, so the 3 over n can multiply the 2 and give you 6 over n, which are all understood to be constants. I can factor all of that out. Don't factor this n out because the -2 doesn't also have a factor of n in the denominator there. Okay, so let's just go from here. So what I did from here to here was I used the sum formula for a constant and the sum formula for I. So it's -2 times n plus 3 over n times the sum formula for I. distribute and simplify. So if I distribute the 3, the n to the n plus 1, and the n over 2, and then the 6n to all of this, combine like terms, simplify, get negative 12 plus 9 over n, which simplifies to negative 3 as n approaches infinity. If you look at the picture, the answer is negative because it's a definite integral, and definite integrals can be positive, negative, or 0. If you look at the graph, if you think of the area below the x-axis as being counted negative and the area above being counted as positive, does it make sense that on the interval from negative 2 to 1 of this function, the total area would end up being negative because there's more below than there is above? So definite integrals can be positive, negative, or 0. All right. So for a definite integral to be interpreted as an area, the function f must be continuous and non-negative. In other words, it has to lie above the x-axis, as stated in the following theorem. The definite integral as the area of a region, if f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a, x equals b, is given by area equals the integral from a to b of f of x. In other words, all that they're doing is saying that the region goes from a to b on the x-axis, and it's underneath the curve, and it's trapped between the curve and the x-axis. Okay, so you always draw your area going all the way down, or your region all the way down to the x-axis. All right, an example of theorem 6.5, consider the region bounded by the graph of 4x minus x squared in the x-axis. Because f is continuous and non-negative on the closed interval, the area is given by the definite integral from 0 to 4 of 4x minus x squared dx. However, you can evaluate a definite integral in two ways. You can use the limit definition, or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, a triangle, semicircle, trapezoid, so forth and so on. All right, so let's look at a couple here. Sketch the regions. So let me just back up real quick. So all I wanted to do was define this area as a definite integral. I didn't actually have to find it in this one. That's why we stopped with this. Okay, so sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. So this is the integral from 1 to 3 of 4. So that would be the area under the graph of y equals 4, bounded by the vertical lines x equals 1 and x equals 3. Okay, so it's the vertical line y equals 4 and the area from 1 to 3 underneath it, which is a rectangle of height 4 and width 2. So that's just the area of the rectangle equals the area of the region under this curve, which is just 8. For part B, x plus 2 in the region from 0 to 3 is a trapezoid. So a trapezoid, the area formula for a trapezoid is 1/2 the height of the trapezoid times the sum of the bases. Now the bases are the sides that are parallel. So this is a base and this is a base. I know you'd probably think that this from 0 to 3 is the base, but that's actually the height. Okay, so it's 1/2 times the height, which is 3, times the sum of base 1 and base 2, which are 2 and 5 respectively. So if I multiply that out, I get 21/2. So the last one, 4 minus x squared underneath the square root, is a semicircle of radius 2. So it's half of a circle. So the area is 1/2 pi r squared. And even though there's a 4 here, that's actually the diameter. So the radius is just 2. So it's 1/2 pi times 2 squared, or 1/2 of 4 pi, or 2 pi. All right, so I hope that was helpful to you. Stay tuned for the next video.